Session 1, Introducing Container Technology. My name is Raman Sangwan. Learning objective of the session is describe how software can run in containers orchestrated by Red Hat OpenShift container platform. That should be the outcome. After you complete the session, you should be able to describe how software can run in containers orchestrated by OpenShift container platform. Linux containers. Linux containers, how you define them? They are an operating system level virtualization method for running multiple isolated Linux systems or containers on a single control host. This is the definition. So individual machines and a containerized machine or containerized application. The difference between a virtual machine, by definition, virtual machine is like independent house. Nobody else will get into your house and you have complete control on the entire plot, the building and the features. Similarly, on the virtual machine we have hypervisor, we have infrastructure, the physical infrastructure, the operating system and the hypervisor and the guest operating system machines. Actual objective is running the application with binaries and libraries and configuration dependencies and all. So application 1 running with the binaries and libraries and dependencies on guest operating system, application 2, application 3. For that, one require Windows machine, one require let's say Mac machine, MacBook, and Mac or operating system as OS X, and another might be Linux machine. Containers are like this building. This is the entire floor is independent, but then on this floor we have multiple apartments. This is one apartment, this is second apartment and third. They are isolated, but somehow they are connected. This is a very good understanding, to understand the difference between containers and the virtual machines. So in this container example, what we have is the infrastructure, physical hardware, operating system, and then we run a container engine, where each application has its own dependent area where it will run with the binaries and libraries and dependencies. That gives you isolation. So in a way you are isolated, but then you are also connected and you are running on the same hardware. The difference between the two, comparative study. Security wise, virtual machines are more isolated. Containers are less isolated. Size wise, virtual machines are in gigabytes, GBs, and containers are in megabytes. Provisioning time, virtual machine take few minutes, but then containers take few seconds. Operating system is more flexible, virtual machines are more flexible and containers are less flexible. Now, kernel. We need to understand few basics in order to understand the concept of containers and how OpenShift concept is implemented and how containers work. So this is basically, this session is about the containers technology. Alright. So, creating regular Linux processes in kernel, how it happens. Normal processes are created, destroyed and managed with system calls. Like there is a system call called fork. Think of Apache. Similarly, exec, exit, kill, open, close, system. These are all system calls. And the user shell make system calls like fork or exec and create a regular process. This is a regular process. The call is made to the kernel responds and the regular process is created. If we talk about containerized Linux processes, then how it works, how it happens. What is a container anyway? No kernel definition. If you talk about from the kernel perspective, there is no definition, because kernel talks about only the processes. So what is the best possible definition? It is a clone. It's the closest definition we can have. And this process create namespaces for kernel resources like mount, UTC, IPC, PID, network, user, everything. So regular processes are created by fork and exec, and clone creates a clone where containerized processes are running. That's the containerized process creation or container creation to be precise. Kernel namespaces are all you get with the clone system call. Like if you are in the user space, if you have a file, normal file cat etc/host, and you make the system call, you will get a PID, you will get user ID and net associations and bindings and everything. But if you are using Docker to run the same command, Docker run cat etc/host, so it will run in the containerized application. So what you will get? You will do a clone system call. So you will get a namespace. This is the namespace. Under that you will get the same thing: PID, UID, and net. So what is different? Different is this namespace. So clone system call create namespace for your containerized application. Container engine provides an API, prepare data and metadata for run C. Three major jobs: provide API for users and robots, pulls images, decomposes and prepares storage. Prepare configuration, passes to run C. So regular processes, container application, containerized image, there's a process running Docker D, container D and run C, which are creating your entire container engine where containerized application and processes are running. This is the call which is made to the system D and how containers are created. Pull image, mapping image layers, pulling, caching and running containers. Most container engines use graph drivers which rely on kernel drivers like overlay, device mappers, etc. There is a work going on to do this in user space, but there are typically performance trade-offs. So in container registry, what we have is we create images, we manage images, we push images, we pull images, and then using these images we create containers. So container repositories have image layers because every container may require multiple images. The important point about the images is they are read-only layers. So another image layers, so keep on adding the layers. So whenever you create a new image out of an existing image, what you do is you add an extra layer, read-only layer to it. And these image layers, when you have a containerized application with multiple image layers, what you do is when you are running it, you add a graph driver and you add a write layer, that is file system layer on the top of it. So what you will get a running container which essentially have a read write layer added to that image layer, and that's how images works. Prepare storage, copy on write and bind mounts. Understanding implications of bind mounts. Copy on write layers can be slow when writing a lot of small files. Bind mounts data can reside on any VFS like virtual file system, let's say NFS or XFS. So here we have MySQL D mounted on root, copy on write. MySQL D another running, copy on write, read write, and then varlib MySQL bind mount read write. And the file system, here we are using the read write layer, and rest of the processes are running in read only part, the image part, as I'm talking about this part, and the extra layer is added. So container image is always read only. When you image is always read only. When you run it as a container, you add a layer to it which is read write layer. Prepare configuration, combination of image, user and engine defaults. Three major inputs. User inputs can override defaults in image and engine. Image inputs can override engine defaults. Engine provides same defaults so that things works out of box. So CLI options, when you pass on, you have user configuration, image configuration, engine configuration, which are stored in the form of config.json file. So we have image layers, and the container engine uses these image layers, add graph driver and root file system directory is created. Then we have OCI runtime default or runc open container interface, and runtime container is running in the kernel space. Prepare the configuration plus CNI. Regular processes, daemons and containers all run in side by side. In action, it takes user specified options, pull images, expand them, and parses metadata of the images. It creates and prepares CNI cron jobs. Add CNI blobs and environment variable to one or more plugins, bridge, portmappers, etc. So image configuration, and this is how prepare the configuration plus container, how containers start running. Engine, runtime, kernel, and more. All of these must revision together and prevent regression together. So Linux kernel container host have regular processes running, orchestration node, container engine node, containerized processes by creating by this container engine, that is container runtime using system D. Plus CLI options, where we have image configuration, user configuration, engine configuration, and CNI config blob, and through CNI plugins. Container orchestration. Orchestration is basically what? Orchestration is systematical, methodological way of putting things together and managing them together, managing operations together. So they have a complete life cycle, and we manage the life cycle of multiple objects which are put together to meet one common objective. Kubernetes and OpenShift. What is the relationship? It's basically the difference is a 10-ton dump truck that handles pretty well at 200 miles per hour. That's how you can think of. Two major jobs. One is scheduling, distributed system computing, resolving where to put containers in the cluster and allowing users to connect to these containers. Provide an API can be consumed by user or robots. Define model state for the application. Completely new way of thinking. So we have RHEL 7 or RHEL 8. We have image layers, repository. We pull the images and we run that like system administrator do the scheduling and defining the applications, and the users and developers access this using application definition. Scheduling containers, defining the desired state, required thinking in a completely new way, like think of a distributed system. Fault tolerance must be designed into the system. So developer or administrator using load balancer, OpenShift master, API controller scheduler, etcd, where database is stored like key value pair database, distributed database, kernel space, and the user developer directly using CRIO and runc accessing the container, scheduling the containers, defining it, wherein images are stored into storage with the NFS store and registry service, and the containerized processes are using these registries or storage to pull the images and run the container. Container standards. The problem is with no standard, there is no way to automate. Each box is different size, has different specifications, no ecosystem or of tools can form. Like just think of this. Different sizes, each one of them. This image is boxes manually loaded on a trains and ships in 1921. Why standards matter to you? Because of multiple reasons. First, they protect customer investment. Second, the world of container is moving very quickly. Protect your investment in training, software and building infrastructure. enable ecosystems of products and tools to form. Cloud provides software providers, communities, and individual contributors can all build tools. Allow communities with competing interests to work together. And there are many competing interests, but then as a community we have common goals. Similar to real shipping container example. The analogy is strikingly good. The importance of standard is critical. Features are catastrophic in a fully automated environment such as port in Shanghai. Think of CI/CD, continuous integration and continuous deployments. Like for example, this hook is ISO standard. This base is ISO 1496. Similarly, the dimensions each have standards, and if you follow these standards, definitely then you are having some standards, so that you can manage them well. Something is so simple require precise specifications of interoperability like files and metadata. Think of that. When you're talking about this catastrophic in a fully automated environment, you can think of CI/CD. Something so simple require precise specification of interoperability. Think of files and metadata. Only way to protect investment in equipment and infrastructure. Think of container orchestration and build processes. That strikingly similar. How did we get here so far? 1979 Unix chroot syscall this were added. 79 milestone. In 2000 we started with jails were added, and then Linux server 2001 that project was started. Based on it, in 2003 SC Linux added to Linux machine. In 2005 full reference of Solaris Zone, full release of Solaris Zones came out. And then we had in the same year 2006 nearly, we have process confinement. Then in 2007 we have GPC renamed as the control groups or C groups, and then in 2008 we have Linux Container Project LXC that was launched. In 2008 we have kernel and user namespaces. In 2013 .cloud Python lighting talk. 2013 .cloud became Docker. In 2013 Red Hat Enterprise Linux came, and 2014 Google launched Kubernetes. Then in 2015 OpenShift Red Hat Container Platform 3 came. 2015 standard via Open Container Infrastructure and CNCF Cloud Native Computing Foundation. And 2016 we have this Scopio project launched under the name OCID. In 2016 Docker Engine adds Swarm, which launched the containerized orchestration complete stack of containers. CNI project launched under the name OCID. In 2016 Containers RD Container D project launched. 2017 MOBI announced. In 2017 itself version 1 of image and runtime specifications came, and 2017 Builder released and ships in RHEL. 2017 Docker includes a new container D. 2017 Kata merges clearly Runway project, and 2018 version 1 of distribution specifications. 2018 CRIO generally available in Power OpenShift Online, and 2018 Podman release ships in RHEL basically to deploy containers, to manage containers. You don't need a Docker, we can work with Podman. That's what the entire training will be. We'll be focusing on containers. Docker and Podman both will be used to run containerized applications. Overview of different standards. Open Container Initiative, that is OCI image specifications. Then we have Open Container Initiative OCI for distribution specifications. The same OCI for runtime specifications, and Container Runtime Interface CRI for Kubernetes standards, and then CNI Container Network Interface is for their networking specification standards. Many different standards we have. Working together, standards in different places achieve different goals. Different standards are focused on different parts of the stack: container images and registries, container runtimes, container networking. But then still they work together. Look at this: container registries and container images governed by Open Container OCI image specifications. CRIO manage this Kubernetes and Kubernetes runtime interface. Networking is governed by container network interface. So this way different standards put together work together in order to achieve the same common goal. Workflow of containers: building block of how a container goes from image to running. First, using OCI image specification, we create image layers. Allows user to build containers images with any tool they choose. Different tools are good for different use cases. Then we have a root file system container engine is created with config.json. Container engine is responsible for creating the config.json file and unpacking images into a root file system. Then a runc or a railcar or runv config.json root file system, we have OCI runtime specifications, which OCI compliant runtime can consume the config.json and root file system and tell the kernel to create a container. And then we make a clone system call on the operating system to run the complete containerized application. Tying it all together, these standards are extremely powerful. What inputs from the builder require? CMD entry point environment. Daemon requires override these CMD entry point and environment. Then user can override CMD entry point environment. These are inputs. What examples? For example, Docker builda, OMOCI. Similarly, daemon process, Docker daemon, CRIO or RKT. User, Docker run, -v data, kubectl run, environment variable or OC. So these are user. So examples of what inputs require, what examples for builder, daemon and users, and then the files requiring for each stage. These are examples: OCI image specifications, then for daemon, root file system, container engine which makes this thing, root file system and all. Finally, starting the container require this containerized application running, and which finally make the clone system call to make your container running. So this is your container running. That's all for this session. I hope you enjoyed it, and that was definition about container, introducing the container engine. Thank you so much for watching. Bye bye.